because I'll forget to do it later. There's going to be some useless stuff at the beginning there. That's all right. Okay. Mm. Okay, no problem. Yeah, no problem. No. There we go. All right.
What are you doing? What are you doing? I watched like half of this. Yes. Why they gotta cut off the front? Oh, hey. Let's go, me too. What type of I do. What type of react? Is it endothermic or exothermic? No, it's endothermic. No, we have bond form exothermic. On base is endothermic. It's like the only part of you get what you can mental philosophy. The part you know, and we wonder how long. Like what are other hard. No, that's what Simon. Young one. Young principal was like,
Hi. What
why you? Okay, bro. Okay, dude. Wait. You and Simon.
okay. You know what? I will post it online. So, because I don't have it ready. Okay, thank you. Okay, you're welcome. Thank you. Okay, we are at 08. So I'm going to give this one more rinse and then we will get back to business. And actually, Norman, could you get the door for me, please? Or Matthew, one of you? Thank you. Norman looks like he's fallen asleep. No, he's probably just got earbuds in. He's got earbuds in. All right, so we now have our solution, which is halfway to be made. And it didn't quite all dissolve, so I'm going to give it another quick shake. And hopefully that'll take care of the rest of it. And if it doesn't, what we can do is just add a little extra water and give it another good shake. So let's do that. because I do want it to still be shakeable while I am trying to dissolve, but it will dissolve easier if I've got more water compared with my solute. Solute is the stuff getting dissolved, and that looks like it's pretty much done it. Yep, okay. So now we have our potassium dichromate, which is this lovely orange color. What do we have to do now in order for this process to be finished? Don't have to increase the temperature, not just yet. If it wasn't dissolving, I would have to increase the temperature. It is not at 500 milliliters yet. My 500 milliliter line is here. So what do I need to do? Fill it up some more. All right, so I'm going to do that. Like I said, normally we would use pure water, but our distiller has gone on the fritz. It's not working. So we're just using regular water. Vancouver water, Burnaby water, has very little in the way of dissolved minerals. So we're actually pretty good. They call it soft water. Water that has lots of dissolved minerals is called hard water. And it usually tastes a little funny. Oh, it's totally drinkable. In fact, it's not bad for you, right? It's got like dissolved calcium and magnesium and all these sorts of things that you need. It just sometimes tastes a little funny. I remember going to my grandparents when I was a kid. They live in Salmon Arm, or they lived in Salmon Arm. I guess they don't anymore. And the water always tasted disgusting. I was like, oh, that's so gross. Yeah. Yes. Yeah, we've got some friends who have a place over on Galliano, and they just bring in water, like those big, those big things. Yeah. All right, so we're filling it up to the line, and I am going to use a beaker. However, when I start to get close to the line, if I go over the line, what do I have to do? If I go over the line, I'm kind of screwed and I have to start all over. So if you go over, you have to start over, which really sucks. So instead of using the beaker for this last, centimeter and a half or whatever, I am now going to use the wash bottle, which sprays at a much slower rate. And that's going to let me, and I'm just going to get my eye level down here and just fill her on up until the bottom of the meniscus is right at that line. Oh, that's good. Okay. Now, I'm right at that line. Am I done? No. Is the concentration up here going to be the same as the concentration down here? No, because I've just added a whole bunch of water to the top, yes? The dense solution is still hanging out at the bottom. So what can I do? I gotta mix it. And so I'm gonna take a stopper. All right, this is a ground glass stopper. I'm gonna put it in the top. And when I do that, it allows me to turn it upside down and get a good mix going. And you'll see little swirlies in there. Have you ever seen swirls when you mix salt water and fresh water? If you have not, go home, make a glass of salt water, just dissolve some salt in some water, and then take a glass, like stir it up really well, then take a glass of fresh water and just look what happens when you mix the two together. You'll see all sorts of little like swirly refraction lines. I don't know what they're called, but it looks pretty cool. And I'm just gonna turn it upside down and right side up. This process is known as inverting. I invert it. And so I do that several times in order to make sure it's thoroughly mixed. And then I am done. And I will just, a bit later, I will pour it into its container here, but I'm not going to waste time right now because we want to get out of here. Okay? So let's write down those steps. So what did we do first? What should we do? Who? We did, but I'm going to actually not go back that far. I'm just going to do the actual physical procedure. We placed the beaker on balance, press tare. You wouldn't write it like this for a formal lab write-up, but we're going to go quick, okay? Then what did we do? Yeah, measure out solid into beaker. Then we put it in the volumetric flask. We will transfer solid to volumetric flask via, that means through, or by way of, what's that? Oh, you travel via, like you can travel via train, so you're traveling by train, yeah. Funnel. What kind of funnel? A wide neck funnel. Also known as a powder funnel. Also known as a powder funnel. Or, once that solid was in there, what did we do next? Yes? Yeah, we wanted to make sure we rinsed out the beaker and the funnel into the flask. Step number 5. Once we had rinsed it, fill the flask about how full? Halfway full-ish, right? Halfway full. And then what did we do? Swirl. Swirl to dissolve the solid. Add water. Until close to the line. Use a wash bottle to fill the last little bit. Yep, we're going to stopper the flask. And we are going to invert, which if you know the definition, you don't need to write the definition, but it means turn upside down and right side up. A few times until thoroughly mixed. If you're going on to university in the sciences, you will probably have to take a chemistry lab, and this is a skill that you will want to have, so because it's a super useful one, okay? What's that? Which what, who? Oh, making the solution, like the whole solution, the whole making of the solution, not the inverting. That's just yeah. So yeah, just being able to make a solution, also being able to do dilutions, which we'll look at a little bit later in the course, is also really useful. Yes? No? What? Uh-huh. You know what, it really depends. Some of them have fill in the blank sheets for first year because they found it's easier to mark. Some people, they make you like write out the whole thing. It's really hard to say, like in terms of the format. But what you do need to be good at is figuring out what the teacher wants and doing it that way. You know what I mean? Yeah, readjust, but be really aware of what is wanted of you and to do it that way. Yes? So anyway. Okay, so we are now going to go to 2.2a, which is the thing you picked up today. Okay, stresses and shifts. It should say page 20 at the bottom and stresses and shifts at the top. So hopefully you did some reading on this last night or the night before. If you didn't, that's okay. I'm assigning the reading again tonight because I feel even if you did read it once, chances are you did not necessarily understand it. And hopefully after today, it will make more sense. Okay? So we are looking at a stress. Now, do we remember the tube brown gas from last week? Yes? Is this system currently at equilibrium? Yeah? How can you tell? It's not changing at all, yes? What's not changing? What's something you can see that's not changing? The color is not changing. Color is an example, and we're going to write this up here. Color is an example of some kind of property, which is also known as an observable property. And I'm going to put this back before I break it. Does anyone remember that name? You would have read about it at some point in last week. Starts with an M. Macroscopic, that's the one. Color is an example of a macroscopic property. When a system is at equilibrium, the macroscopic properties do not change. Have you died on me, pen? No, you haven't. Okay. Equilibrium. So our tube stayed at the same color. Its macroscopic properties were constant until we did something to it. What did we do to it? We put it in hot water. We also put it under different conditions into cold water. right? What we did to it was the stress. We stressed the system by changing its conditions. We changed the temperature. So that is the definition of a stress. Basically, a system which is at equilibrium is just going to hang out at equilibrium unless you stress it, unless you make some change to the conditions. So a stress, ooh, that was supposed to be a highlighter. That was not a highlighter. There we go. A stress is a change that we make to the conditions of the system. And the whole thing about the stress, ooh, before we do that, what can you say about the forward rate and the reverse rate when a system is at equilibrium? Yeah, they are the same. So the whole thing about a stress is that what it does is it then makes the rates unequal. It might speed up the forward rate. It might slow down the reverse rate. It might speed both rates up, but maybe one speeds up more than the other. So what it does is the stress is making the forward and reverse rates unequal. So the stress makes the forward and reverse rates unequal. Now, for our convenience and to make our diagrams look beautiful, yes, Riley? Oh, okay. So to make our diagrams look beautiful, we assume that stresses are instantaneous, that they happen in no time at all. Okay, in reality, is that the truth? No, it's not, but it makes the diagrams really clear and it makes it really easy to see a stress. So we consider them to be instantaneous, which means they take no time. Yes? Reaction intermediates do not affect rate. Inhibitors, we're not going to worry about inhibitors because they come up very infrequently. But yes, they would also not affect it, but we're not going to bother with them. Okay? Yeah. Now, we're going to be drawing two kinds of graphs in this unit, and one is called a concentration graph, and one is a rate graph. And regardless of which kind of graph you're looking at, the stresses show up as vertical spikes. So literally, like that. Okay, so it'll be an up and down line. Because if on our graph we have time along the bottom, and if we have something like, let's say, rate here, if it's a low rate and then all of a sudden it's a high rate and it takes no time at all, that change has to happen vertically. Yes? Yes. It's straight vertical. In reality, is it straight vertical? No. It would be a short amount of time, okay? So we just draw them straight because we're not too concerned about the details, yeah? Yeah, exactly. So what things can be stresses? Well, it needs to be something that can change the rate because we have made the rates unequal. And you guys already know some things that can change rates, yes? You know that concentration can change rates. And so concentration does qualify as a stress. Hold on. You can't change the nature of the reactants for a particular system. The system is the system. You can just have a different system with a different set of reactants. Okay? Yeah. I don't know why I wrote pressure twice. I think I was going to do it on 2 lines and then I did it on 1 line so you can get rid of that second pressure. But changing the volume can change the rate, and so that can be a stress. And obviously we know that changing temperature can change the rate. So what do these three have in common that the not stresses don't have in common? Yes? Yes, but you'll end up with that with surface area as well. Okay, so the deal is, and I don't actually expect you to know this at this point. Yes? Oh, it's okay. That's only temperature. What the thing is with these ones is they will either change only one rate, forward or reverse, or they will change the two rates unequally. These three change either A, only one rate, forward or reverse, or they change the two rates but not by the same amount. So maybe you have something that speeds up temperature, for example. If you increase temperature, all rates speed up, yes? So you're speeding up the forward rate and you're speeding up the reverse rate, but it's going to speed up one more than the other so that they are then not equal. If you change a concentration, that's only going to affect one of the two rates. We're going to look at each of these in detail, so don't get too excited about it just yet. We're going to go into much more depth today and tomorrow, okay? Or B, both rates, but not by the same amount. And like I said, if you're not quite getting this yet, don't worry about that. It's going to come. We'll do examples for each one. Now, the things that are not stresses, it's not that they don't necessarily change the rates. We know that catalysts do change rates, yes? But they speed up the forward rate and the reverse rate by exactly the same amount. So if you have, your initial setting where you've got your system, now we add a catalyst, both rates get bigger, but they get bigger by the same amount. So is there going to be any change in the amount of reactant and product? No, because you're still using them and producing them at the same rate. Pardon me? Kind of, yeah. So adding a catalyst changes both rates, but by the same amount. So the forward rate still equals the reverse rate. And therefore we are still at equilibrium. And actually surface area, same thing. Okay? Yeah, it speeds up the forward and the reverse because let's say you have a solid at the bottom and it's dissolving, yes? And the equilibrium is for every particle that dissolves, another one precipitates, yeah? If I have a bigger pile of solid, sure, I'm going to have more dissolving, because if I had a small pile of solid, it would only be able to dissolve off that small pile. But if I have a bigger pile, for every one that dissolves, because I've got a saturated solution, right, it cannot hold any more solute, another one has to precipitate. And that'll be unit 3, is when we do that, okay? Now, an inert gas, that one's all on its own. It actually doesn't change rates at all, if you recall that. What does it mean to be inert? unreactive. There isn't. There's no, we don't, it's just like, we try to trick you by saying, oh, we increased the pressure by adding an inert gas. And you're like, oh, we increased pressure, rate increases. But no, if you do it by adding an inert gas, there's no change to rate. The inert gases, those are your noble gases. They don't have any, well, I mean, sure, they have purposes. I mean, if you just look at helium, you can make a balloon float, right? In terms of reactions, though, no. And this does not change the rate at all. So either we have both rates changed by the same amount, or we have the inert gas that doesn't change the rate at all. And today we're really only going to focus on concentration, but we're not there. Oh, we're not there yet. That's okay. We'll get there. Yep, we're good. So we stress the system. When I first put it into the hot water, what did the system do? I increased the temperature. What did the system do? I made more of the brown gas, yes? The system made more of the brown gas. I didn't make more of the brown gas. The system did that. So the system will shift in response to the stress. So what is a shift? A shift is the equilibrium system's response to the stress. How much time did we say a stress took? No time at all, okay? But a shift, oops, I skipped the first point, that's okay, we'll go back to it. A shift always takes place gradually over time, okay? And why is the system shifting? Well, it's trying to get back to an equilibrium condition. So it's going to shift in order to make the forward and reverse rates equal again. So the rates are equal, we stress the system and they're unequal, right? And then it's going to shift until they are equal again. Like I said, shifts take place gradually over time. The shift is fast at first, but then it slows down as time goes on. So what that's going to look like on a concentration or a rate graph is it's going to appear as a curve. Okay, so the shift is going to appear as a curve. The initial slope is steep. And then gradually over time, the slope becomes shallower. Until eventually it becomes flat. Okay? So this area here, where we have the curve, that curve, oh, that wasn't good. It was an eraser. There we go. Our curve, that is where we have our shift. No, that's just showing, no. Oh no, what have I done? Ah! There we go, okay. So this area here is the shift. And now we're going to put it all together. Okay, give me a minute to get that. Okay, so here we have a diagram, sample problem number 1, and the first question is super hard. You're going to decide, is this a rate diagram or is it a concentration diagram? Like I said, it is super duper hard. Is that a rate diagram or is it a concentration diagram? It is a rate diagram. Look, rate. So that is a rate diagram. Don't you wish all questions were like that easy? Okay. That's a rate diagram. And on our rate diagram, you'll notice that we plotted both the forward rate, and on this diagram, it's in red. On yours, unfortunately, they are just gray, okay? And our reverse rate is blue. What is true of the forward and reverse rates during this section of the graph here? Number one, they are staying constant, but also they are the same as each other. The red and the blue are the same. So the forward rate is equal to the reverse rate. So what does that tell us? We are at equilibrium. So we're going to call this the old equilibrium. Do you see a stress? Rade is going to be so sad that you missed this. Do you see a stress on this diagram? Yes. Yep, where is it? After the old equilibrium. Yeah, we got that huge spike. Yes, there is our vertical spike. That is our stress. Okay. And then we have this area here. What's going on in here? We have a curve. What does that tell us is happening? That's our shift. And you can see what happened in this one is that we had our old equilibrium, forward rate and reverse rate were equal. We had the stress, which in this particular instance increased the forward rate. What did it do to the reverse rate? What did our stress do to the reverse rate? Did it? If it were the stress that increased it, it would happen right here. The system shifts in response to that stress, and then it increases. Does that make sense? It's not the stress that's doing an immediate change. We are getting that response to the stress that is then increasing the reverse rate. Yes? The reverse rate at that moment in time, there is no change. Until we start shifting. Yeah, that's right. Okay? So at the moment of the stress, the forward rate increases. And the reverse rate stays the same. Nope, but it's being recorded. So you can check it out online later tonight. Okay? Now, after our shift, what's happening? We're at our new equilibrium because once again, those rates are equal. So that is our new equilibrium. Now you'll notice that they are both faster than they were at the old equilibrium, yes? But they're equal to each other, so we're now at a new equilibrium, okay? And anytime you have a shift, the two rates, which are different, are going to then come back together so that they are equal. That's the whole point of a shift, is that the rates are going to eventually become equal. All right, now I'm going to belabor a point a little bit. Are the slopes at the beginning of the shift, are the slopes steep or shallow? So here's at the beginning of the shift right here. Is that steep or is that shallow? That is steep. I would not be happy skiing down a slope like that. That would terrify me. I haven't skied in years. Now, how about, what does that mean about how quickly the rates are changing? Are the rates changing quickly or slowly? Quickly at the beginning. Are the slopes at the end of the shift steep or shallow? They're shallow, right over here. This is really shallow. That means that at the end of the shift, the rates are changing slowly. We good to scroll? Okay. Sample problem number 2. This is our other type of diagram. Is this a concentration diagram or a rate diagram? Concentration. Gosh, that was difficult, right? That's a concentration diagram. I'm going to get rid of that circle because it's ugly. And you'll notice that in this particular system, I have 3 different substances. We have some NO, we have some Cl2, and we have some NOCl. Presumably some of them are reactants, some are products. We don't care just yet. We'll get to that. During this part here, what can you say about the concentrations of those 3 substances? They are, how do you know they are at equilibrium? Because they're flat. What does it mean that they are flat? It means they are not changing. So the concentrations are constant. So yes, we know we are at equilibrium here because the concentrations are constant. So this is our old equilibrium. We know because concentrations are constant. And concentration is another example of a it could be a stress, but I'm looking for what kind of property? Macroscopic. Learn that word. Okay? Macroscopic. And therefore, at equilibrium, it will be constant. And going crazy, sorry. Can you see a stress on this diagram? Yeah, there's just one. Yeah. Okay, so right here, that right there is our stress. And in this case, the stress is an increase in the concentration of NO. Yes. Yes. Because what's going to happen is eventually you'll have like a temperature change, which is the stress. You won't actually see a spike on the concentration diagram because you can't, it doesn't change the concentrations, right? But you will see the shift. Okay, and we'll get to that next day. Yeah, yeah, yeah. So you'll always see spikes on rate diagrams, but you will not always see spikes on concentration diagrams. Okay? So there is our stress. We had an increase in concentration of NO. So let's say, for example, that, I don't know, let's pretend this is full of gas instead of full of liquid. Yes? And let's say I had a hypodermic needle, you know, like what you get a shot with. Let's say that this was made of rubber and I could stick the hypodermic needle in there. Yes? Inside the syringe is some extra NO gas. So I stick the needle in and I push down the plunger and the extra NO goes into the flask. So that's how we would make a change to the concentration of NO. Make sense? Okay. So that was our stress. Where is our shift? Yeah, well, on this diagram. Yeah, these little curved sections. Okay, so this little blue shaded area, it's the curve after the stress, right? And if there's no stress, then it's just the curve. Yeah. So we have our shift. So that's going to be like this area here. Come on, draw for me. We know it's the shift because it's a curve. And finally, what do our concentrations do? They remain constant, yes. And so we are now at a new equilibrium. Yep. Eventually, you'll always get back to a new equilibrium. As long as your system is closed, right? If you've got an open system and things are just flying out into the atmosphere, you're not going to have that. But okay. Now, one thing that I think I pointed out with my other blocks that I haven't said here yet, when we are at equilibrium, we know that the concentrations are constant, but we should mention that they are not equal to each other. Yes? And you can see that, like one's way up here. The concentration of NO is higher than the concentration of NOCl. Yes? So they are not equal to each other. Now, once again, going to belabor a point. Are the slopes at the beginning of the shift steep or shallow? They're steep, yes? Compared with other areas of the curve, they're steep. This means that at the beginning of the shift, the concentrations are changing quickly. Are the slopes at the end of the shift steep or shallow? Shallow. And that means that at the end of the shift, the concentrations are changing slowly. Why do I keep harping on this? Because people draw the curves wrong all the time. And I'll show you how they draw them that's wrong, and it's labeled wrong, 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 wrong. Okay, but before we do that, the next page is just the answer key to this. There are some typos in it though. I don't know what was wrong with me. Like, I guess I didn't proofread it very much. This should say, and this should say steep. This should say shallow. I don't know. Like I said, if you just cross out this page and use what we did in our notes from the previous page, you will be better off, because this is a nightmare. I'm like, what on earth, right? And this next part here, the beginning, they are steep. That's quickly at the end. These are shallow. I mean, I don't know. I would just cross out that page. You have all the answers on the previous page, yes? So just ignore that. All right, features of the diagram. So everything's just kind of here, all laid out for you to take a look at, both types of diagrams side by side. When a system is at equilibrium, the forward and reverse rates are equal. The concentrations are constant, but not equal. On our diagrams, a stress is signified by a vertical spike or a vertical line. Spike. Oh my God, what's wrong with me? I think line and spike are trying to get out of my pen at the same time. Spike or line. There we go. I've managed to separate the two words. And a shift shows as a curve. Now, this is why I've been harping on the shallow and the steep and all of that, because this over here on the right-hand side, that's what I see all the time on quizzes and tests, right? What is this saying? This is saying I had a stress, and now the concentration changes slowly, then it changes quickly, then it changes slowly again. Is that a happy thing? No. So this would be slow, quick, slow, which is wrong. Yeah? What you want to see is you want to see quick, then slow. So what that means is if you have a quick rate of change and then slow, you're going to see these sharp points. Yeah? And in fact, you can draw dots on there for yourself to kind of be like, oh, that's where it should, that's like the elbow, right? Pointing out there. An S curve would indicate that the concentration, oh yeah, blah, 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 blah. This one is just showing the same thing on a rate diagram. Again, this would be slow, quick, slow, which is wrong. And then finally, when we show the new equilibrium, the one on the left is good, the one on the right is not good. What is wrong with the one on the right? It curves up. It's hard to draw these things. If you're just drawing in your own notes, it really doesn't matter. You can be like, I know that's supposed to be a straight line. It's all good. On a quiz or a test, you are going to use a ruler, and that way you won't end up with those. Okay? Is good? All right, I think we are done that. I'm just going to skip over that last bit. We need to go on to 2.2b. I know you're like, oh my God, we're doing what? Yes, we have 7 more minutes and we're going to do this. Here we go. Whew. Stresses make the rates unequal. Shift makes the rate equal again. Yay, we knew that. Here is our system that we are looking at. We have H2 plus I2 gives 2HI. If this system is at equilibrium, what can we say about the forward and reverse rates? They're equal. So if we were to draw this on our rate diagram, we would say if my forward rates is my solid line, and my reverse rate is my dashed line. How should I draw those two lines if I'm at equilibrium? Right next to each other. Across we go. Boom. Boom. Okay, there we go. Now, if I increase the concentration of H2, and I'm just going to rewrite our equation here so that we don't forget. That's going to be our stress. We have increased the concentration of H2. What happens to the forward rate? It does, but what specifically happens to the forward rate? Which direction? Yeah, the forward rate increases because we have more collisions between H2 and I2. There's a greater frequency of collisions between H2 and I2. BW is between. So what would our rate diagram do? At this point, we would have our forward rate, we would have our reverse rate. And what's our forward rate doing right at the time of the stress? It's a vertical spike. Yep. Now, what about our reverse rate? Is it going to change right in that moment? No, in that moment it stays the same because we haven't increased the collisions between HI particles. So it just stays there. Okay. Now, the next question is just to let you know what the term, it means to favor a reaction. If we say a reaction is favored, that means that that particular direction goes faster. So, which reaction is favored, the forward or the reverse? Forward. Okay, excellent. Carrying on. We're almost done. Oh, we might just make it before the bell. Okay, as a result of the forward rate being faster than the reverse rate, and I'm just going to draw what that looks like up here. We have H2 plus I2, and we're going to make the forward arrow really big, showing that it's fast. And we're going to make the reverse arrow much smaller, showing that it's not going as quickly. So now we are shifting. As this shift occurs, when the forward rate is greater than the reverse rate, what is happening to the concentration of H2? We increase the H2. Now the forward rate is greater. So we are using it up faster than we are producing it, yes? So we are using up faster than producing. So what will happen to the concentration? It's going to decrease because we're using it up faster. How about I2? Hold on, I2 is on the same side as H2. So it's also going to be used, yeah, up faster. Okay, so it's also going to decrease. Now what about HI? That one's going to go up because it's on the other side. We are making it faster than using it. So now, we now have, since H2 and I2 are increasing, no, they're not increasing, they're decreasing, sorry. What happens to the forward rate? Yeah. The forward rate decreases. So on our graph, what that's going to look like, we had our equilibrium, we increased the forward rate by increasing H2. Now we're using up H2 and I2, and so that forward rate is now decreasing. Oh, look at that. Isn't that what we wanted? Yeah? We also know that the concentration of HI is increasing. Therefore, what happens to the reverse rate? The reverse rate increases. And so, oh, look. And what's happening? Those two rates, they meet in the middle, so the rates are now equal again, which was the whole point of the shift. Your homework is to reread 2.4 and see if you can understand it a little better this time. If you totally understood it already, then God bless, you have no homework tonight. Woo! What? 2.4. No. 2.4. No. 2.4 in Hebden. Hebden. Yes. Hebden? Hebden. Read it again. We made it.
Did I get out of 2.1?
Yes. Oh! Yeah.
It just says that I'm going to be away next week for my, just at the bottom right here, for the double block, because I'm getting my food safe certificate.
Oh, good for you. That's excellent.
Awesome. Thank you.
Not there. Oh, it's promising. Electrochem, no. Matthew, I'm not sure what I've done with it. Tomorrow. Testing, 1, 2, 3. Hey, it looks like we recorded. That's good. Okay, bye.